This is the output from VAR estimation we've seen last time. And I mentioned the way we select optimal lag for the VARP process is to check this information criterion. Right? So, for instance, because we are dealing with multiple equations, now things are now covariance matrix instead of variance, but the number will be a single number, scalar. So archaic information criterion or a Schwartz criterion, you can choose either one. And we've seen previously that some criterion find a smaller lag. On the other hand, the other criterion may find a longer lag. Okay. But I mentioned in many cases, many applications using Korean data, Schwartz criterion appears to be working better than archaic information criterion. Okay. The way we produce a future path of the variable included in the vectorial regression is to simulate the model. If you want to, let's say, assuming VAR1 process, if you want to calculate the future value, let's say S period apart, then you can recursively calculate this thing because X could be data, C and A are coefficients and intercept, so you can recursively calculate this analytically. So all you do is to calculate conditional expectation, which is same as univariate time series forecasting. But when you actually, if you're interested in calculating this type of confidence band as well as mean forecast, then later I'll show you how to do this using bootstrapping. So let's move to, because we've seen this one already, so let's move to this bootstrapping. Well, actually, if you are willing to assume that fitted residuals are distributed multivariate normal, like this one, you can draw a vector of residuals from this distribution. Okay. So it's not that difficult. Let's see. Where is our simulation? Oh, right here. To simulate this, you can draw this vector in the future period from multivariate normal distribution, or you can bootstrap those residuals, which is very similar to the procedure explained for univariate simulation model. So you can recursively calculate this X, and then you can find relevant confidence band. Right? But one thing to remember is if you want to generate, let's say, the value at t plus 1, where you are at time t. Okay? Of course, C is fitted value, intercept vector, right? So this is known. And A1 hat is also known. And XT is current data, right? And the question was how to draw this number, right? So our strategy is to at, let's say, period 1, 2, 3, and then vector of fitted residual, right? At period 1 and also 2 and so on, right? So when you draw numbers from this fitted residual to bootstrap this, you are not drawing single number random fashion. Instead, what you do is you draw this whole vector in a random fashion. Can you guess why we do that? Why we not? Well, this is error vector at time period 1, right? Error vector time period at time 2, and so on, right? Why not just put all those numbers in a single urn and draw numbers? Instead, why do we draw this number as a vector? Can you guess? Well, the reason is, the epsilons, this error vector, we assume that it has covariance, right? Omega, right? By drawing these as a vector, you want to preserve this covariance structure, right? Why do you observe particular realization of epsilon? Well, it reflects covariance structure, right? So if you just draw random numbers, then actually you are destroying this covariance structure, which is not consistent with your model, right? So you have to keep this feature by drawing vector instead of single numbers. Okay. This is the assignment 2. There is a part 2 of this assignment later. And this lecture note is slightly updated, the revised this morning. So you may want to download the later version of this lecture note 5. I uploaded text file, GB data, which contains Korean Treasury bond spot rate series with maturities 3 months, half a year, and so on. Okay, so up to this many. Data will covers the period from September of 2000 to September 2012. Okay. So first, try to fit VAR model, okay, using, let's say, shorter period, okay, and then generate dynamic forecast for the period. This is our out of sample period, okay, and compare historical values and your forecast. Okay, so the result will look more like this one. You're estimating this VAR model using data up to here, leaving these as historical out of sample, and then generate a forecast and the band, and then plot this along with that. Right? When you actually do that, this is an example of, let's say, spot rate, right? This one, let's say, here's one, another, another. When you actually estimate this model, let me remind you that, let's say, using up to 11, when you estimate this, first we want to make sure things are stationary, right? But we want to generate forecast in terms of level, right? So the way you do it is to if you call, let's say, spot rate as S1, S2, S3, and so on, you should type this one as the first element in your vector X. Okay. So in that way, when you generate a forecast, then it will calculate S1 and its forecast. Right? Similarly, S2. Let's try this, the 3 only, okay? And this is the lag specification. So 1, 1, or 1, 2, 1, 3, 1, 4, right? So let's try 1, 1. It says near singular. Why is that? Let's check data first. I wonder. Are different, right? S1, S2, T, S3. Like this. Probably I typed the same thing. So it says singular. So what you do is you check this number, right? And select P. And then when you are done and you're satisfied, then you can try make model, right? And solve. Stochastic. You want constant span, right? And here is your out of sample. And you can change this one as, currently it is set as 95% constant span, right? You can change it to 50%, 60%, as you please. So let's leave it there. And we know that there should be accidentally I plotted this S10 as well, right? So you don't need this one. Oh, sorry. So suppose you did that. Here is 1, high, low, medium, open. This is your result. Okay. So if you are not so sure, go back to the selection notes in file, okay, from our classroom in a portal, and try to follow this procedure. Okay. So probably, you know, when you create your own walk file, the procedure I recommended, you can do it in, you know, this type of thing in several ways. So first you have to create this walk file, right? So what you do is, let's say x1. This is, let's say, my first spot rate, and then I can say NA series. The second one is NA. And if you keep doing that, and then you bring this 2 as a spreadsheet, right? And then you press this edit plus minus, now you can copy things here, right? But the problem is GB13, this thing, is in ASCII, text file, right? In text file. So, well, if you're lucky and have this type of editor, then you might copy this, right? And then paste it right here. Oh, did I see? Like this, right? But if you don't have it, then, you know, there should be another way of doing it, right? So, from my experience, you know, convert this text file to, let's say, Excel file. Then you can easily, you know, cut and paste things, right? So, this one, actually the same data. So you can copy this 3. Was it 2 or 3? 2. So you can copy, let's say, this data to right here. Okay. And when you are done, press this one again, and now you are done. So you can play with this one. So taking first difference is one thing to make stationary, and the rest of them is just, you know, just clicks away. Okay. Okay. Now, this is the portion that hasn't been included in the previous lecture note, but it is now in. What I'm trying to explain here is, let's go back to previous macrofinance model here. As I explained previously, F1, 2, 3s are like level, slope, curvature of term structure, and these are macro variables. Okay? So if you fit some model like this one, and of course, you can build your forecast, right? Also, what you can do is here what is called impulse response function. Okay? So impulse. So let's try this and press it. You see many graphs, right? So what do we got here? Well, the way we read it is like, this is for first equation, second equation, third equation, we have 8 equations, right? And what this graph means is, suppose there is a shock to first variable. Then, because we have a vector autoregressive structure, it will affect future value, right? If there is a shock today, then it will affect future value, right? So the shock to the first variable will affect the first variable in the future, right? So that's this part. So what it says is, immediately it will increase the value, but the effect will be dissipating. Right? The shock to the first variable will affect the second variable to the negative direction, but it will dissipate, right? And so on. Right? What this graph means is shock to the second variable on the first variable, effect on the first variable, and the second variable, and the third variable, and so on. Okay? Then how to calculate this thing? So let me explain it from here. The impulse response function is, in this vector framework, is very similar to univariate case. Because it's vector, if VAR P process is stationary, then you can always find infinite order vector moving average process. And let's say the shape is something like this one. In a univariate time series model, we call this type of representation as world representation. Any stationary time series can be expressed as linear combination of all residuals. Okay? But now this is vector. So this is a vector, and this is a matrix. And the psi1 is defined in terms of something like this one. So suppose someone calculated psi 1, 2, and all those numbers after fitting this type of model. Okay? Actually, the calculation is a little tricky, but the computer will solve it for you. So let's say if you pick psi at S lag, S, but this number, actually this is matrix, means if there's a shock today, that's the impulse, and then response. Because there are n vector, n elements in this vector, so shock would be n of them, right? And also the variable, it consists of n elements, so this could be n times n matrix. So if you set this one as S equals to 1, 2, 3, 4, S equals to 1, 2, 3, 4, 5. And these are the plot of this psi, relevant psi. Okay? But let me add a few more things here. Actually, the one you've seen in EBUS is not really this thing. It has some problem. The first problem is this result, or we call impulse response function, is very difficult to interpret because we say residual terms are contemporaneously correlated. What that means is, off-diagonal terms in covariance matrix are not zero. So what I mean is, let's say you have many numbers here. These are covariances, right? So suppose this one is positive. So 2, 1. This covariance is positive. So if there is a shock in the first error term, will affect this, right? At the same time, this one, because this is correlated positively with the second one, this will change, right? So if there is a shock, it will affect this one directly, and also it will affect this one through this positive correlation. This one will increase. Okay? And then that's going to affect this one as well. So we say direct effect and an indirect effect. Right? So we don't know which one is which. Right? So this appears to be problematic. So one way to deal with this problem here is to transform residual terms. First transform it, and then compute something called orthogonalized impulse response function. So cutting this type. Cutting this type. So how we do it? We use method known as here Cholesky decomposition, which is this. If you have symmetric matrix, like covariance matrix, you can estimate from VAR regression, right? So if you are given some symmetric matrix like this covariance matrix, what Cholesky decomposition means is you can decompose this one as product of two matrices, where S is lower triangular matrix. So when we say lower triangular matrix, the main diagonals are all 1, all unity. And this side is all 0. And this side, some numbers. That's lower triangular matrix. And this is simply the transpose of that. So upper triangular matrix. So you can, there is a way, particular way of doing it. It's also known that you can find some matrix like D or A, so that later half of this and half of that corresponds to this one. Where D is a diagonal matrix, so it has numbers on main diagonal only. Off diagonal terms are all 0. That's diagonal matrix. And A is lower triangular matrix. So let me show you how this A matrix looks like. So, first step here, to transform residual, right? How you do it? Well, mechanically, when you decompose this one into, let's say, this, and actually you can calculate this A. So A, and then define new residual as original residual vector multiplied by inverse of matrix A. Or you can multiply both sides by A, and that's the expression here. A times U equals to E. Okay. So why we calculate this U? Well, U is now orthogonal. U is, of course, U1 equals to this, right? What is U2? This times that plus this, right? So this one is stationary. So this one is also stationary because it's a linear combination of this and then this. So all expectation of U is 0. And then this is the variance formula. So variance in matrix notation is expected value of U vector multiplied by U transpose. Then because we define this one as A inverse ET, and this is known constant, so it go outside this expectation operator, and similarly for this one. And we know that this one is simply this one. Right? So if you go through this, then you end up with the diagonal matrix. So this U is all orthogonal each other. So if you calculate from this omega, from that omega to this A matrix, then Cholesky decomposition will return these numbers. And if you define U in this way by multiplying A inverse times this one, then these have no covariance. Because as you see here, the covariance matrix is diagonal matrix. Right? So no off-diagonal terms. Right? So this is what we call orthogonalized residual. And now the calculation is, what if there is a shock to U? So transform the residual, the shock to that on the future path of X. And that is computed as previously calculated psi times this AJ is jth column of matrix A. Jth column. So calculation may look awful, but luckily the DBs can calculate this one for you, so you don't have to worry about. But this is not the end of the story. In practice, what we do is something like this one. Not with respect to U, instead another one, V, where V is defined as UT multiplied by this one. So what is D? D was the covariance matrix, right? Diagonal matrix. And so it has all numbers here and then all 0, right? So what is D to the power half minus half? That means you're actually taking square root, right? Square root, square root, square root. So that corresponds to this one divided by standard deviations. So it is standardized residual, right? So orthogonalized residual and then standardize it. Why do we do that? Well, because those elements in vector X may be measured in very different unit, right? One in billions of Korean won. The other one could be in percent. The other one could be in decimal. So all have different scales, right? So when you are trying to say, let's say there is a one unit, there is a shock to first variable, then if you increase this number, let's say the first number by 1 unit, may have different meaning as changing 1 unit here. So if this one is measured like something like 2, 1, this kind of decimal scale, but this one is measured by usual scale like this one, change in this value by 1, change in this value by 1 are very different, right? So you want to standardize these numbers using their standard deviation to make it comparable. So even though we say there is a 1 unit shock here, but the correct statement is 1 standard deviation shock. So 1 standard deviation shock here could be raising it by 10. 1 standard deviation here could be raising it by 0.05, for instance. Okay? Because they have different scale. Get the message? So the result you see is mostly this one. Okay? Well, we want this one is the end of the story, but the thing is not. There is a last problem. What is U, orthogonalized one? Well, this one, the first one are the same, right? The same. The second one is what appears to be residual is added to this product. Right? So it's like this one is perfectly exogenous. So this one is first determined. And when this one is determined, then this one is determined by using this information, of course this one, and this one. So these numbers are determined recursively. Right? The first one being exogenous. So this type of recursive structure, well, you cannot avoid it as long as you find this A matrix using Cholesky decomposition. So if you actually change the ordering of the variable, so instead of first variable putting in the first location here, suppose you put it there and something here. You know, if you change the order of this variable, then the impulse response function may look very different. So it depends on the ordering of the variable. Right? So when this method was first introduced, the inventors of this type of model, Christopher Sims and others, they recommended to set your vector x in terms of something very exogenous to something very endogenous. So let's say exchange rate. Well, 1 versus US dollar. Well, although Korean won has something to do with our economy, it's our national currency, but still the exchange rate is mostly influenced by foreigners. Right? So, you know, you can't simply, let's say you want to make an exchange rate from current like 1055 to 1100. You can't do it, right? You have to spend a lot of currency reserve to, you know, manipulate that kind of exchange rate. So it is very difficult to influence that, and so we say exchange rate may be exogenous to our system. Then, you know, foreign exchange rate could be set here. Okay. And how about interest rate? Interest rate, let's say call rate is very close to our policy rate set by the Bank of Korea. And the call rate or policy rate is set, but you know, each month we try to forecast whether the BOK will sustain current policy rate or increase it or decrease it. You know, we make a lot of guesses, right? But usually, you know, sometimes it works, sometimes it won't. So we might think that, well, this one is also exogenous, set by monetary authority. Okay. And then others, and then let's say GDP. Because of this is determined. The story was like that. But still, it's also arbitrary, right? It's all arbitrary. So if you want to build a model and do this type of analysis, our recommendation is to try to find something more exogenous first, and then the variable of your interest last. So if stock price could go here, right? But if your focus is to see the effect of this on stock price, then probably you may want to put it right there, assuming these affect that. Okay. But there is also a good story here. Pesaran and Shin in 1998 proposed a new method, which is called generalized orthogonalized impulse response function, or IRF. It's a typo. Yeah, this one. And if you go through their logic, you can see that if you calculate this generalized ORIF, actually doesn't matter how to order elements in vector X. So in that sense, it is generalized. So usually we report that number and don't worry much about ordering things. But still, you may want to put something of your interest, your focus variable last, and exogenous one first. Okay? So let me show you standardized ORIF, which is this one. And using same data, this one, the second one. So here is the first one. Here is the second one. Look similar, different? Okay, let's focus on this one, the last one. So this is a 4x4. So we have 4 variable system. Shocks to the first variable, and it's the response of first variable, second variable, third variable, fourth variable. Okay. So let's focus on this one and see if there's a difference. A little, right? In this case, a little. Okay. But if you look at other examples, you might see some difference. But the way we interpret this one is, let's say, by the way, this dotted lines, that's the Compson span of this number. Because this number is calculated from this matrix, right? But this one is calculated from this matrix, which is estimated. So this is uncertain, so uncertain, so uncertain, right? So it has to have a band. So without this band, you can say, well, literally it pushes up this variable, the shocks to this variable, pushes up and then positive and then die. But what it says is, lower bound and upper bound covers, point of 0. So this is numerically positive, but statistically 0. So positive effect lasts only a few periods and then quickly die off. Similar. Yeah, very similar, right? And also, let's see, impulse. where is forecast decomposition? We used to have that. So let's not. I don't see it from this version, but let me briefly mention what this means. If you make a forecast, then this is the forecast error. Sorry, actual value. So this is forecast error, right? And you can calculate mean squared error, or we just call it forecast error variance, using omegas and psi's. Okay. So in the future period, there is a forecast error. So things are not perfectly right. So there is an error we are making, right? Then we think that where that the difference coming from. So in the future, the difference between this one and your fitted value is from this one, right? But this forecast error decomposition is trying to decompose, let's say, in the first period, let's say, next period, if there is a forecast error, whether that is contributed mainly by, let's say, first shock, second shock, third shock, and so on. And suppose somehow you can decompose that contribution, and suppose it turns out that the variation is mostly explained by itself, then we say that's something exogenous. So let me show you this graph first. What this number means is the first number. This is 1, 2, 3, right? What this number means is forecast error made at, let's say, next period, one period ahead, is explained about, let's say, almost 70%. And second variable, the errors in the second errors of second variable explain almost nothing. The third one, almost nothing, nothing. So what it says is the first variable is just going by itself, driven by its own shock, not explained by other shocks. So it's exogenous. But some other variable, a second variable, its own shock explains about this much. The first shock here explains about this much. So why this second variable fluctuate over time like this? Because of the shock to its own, shock from its own equation, but also other shocks like this one. Okay. So the reason why we do this is to check whether particular variable is in fact exogenous or not. So it appears that the first variable here appears to be exogenous. The rest of them, if you look at it, then some non-zero numbers, all adding up to 100%. But as I said, people do this over and over again. Why? It looks good. looks complicated. It occupies pages, so your report can be thicker and looking beautiful, but you know, it doesn't say much, I think. So I don't do this often, but probably you see it many times in the paper, so you need to know at least how to read this one, right? Okay, this will do for the vector autoregression, and later in the following weeks, we will extend this vector autoregression to vector error correction model, which is more suitable for long-term forecast, as I said. But before we move to that subject, let's cover the method called principal component analysis, which is another way of handling, you know, this type of multiple equation. Actually, there are two related methods. One called PCA, the other one called factor analysis. It looks alike, but let's compare it here. Well, principal component defined here in notation psi is, well, here let's say R1 through N are, let's say, stock returns for company 1, company 2, company N. So R is the data. Okay. So if we have these data and W is the weight, so we call it, you know, technically, this is linear combination. Right? Linear combination, and we define new variable, psi1. If you have different weights, you can determine psi2 all the way up to psi k. Okay? But usually, k is set usually less than n. So here is the you know, very rough idea about what is this principal component analysis. Suppose you have two series. And, you know, let's say you want to forecast, you know, or simulate future path. Well, you have to model this one as a VAR, two-dimensional problem, bivariate model, or you can apply univariate time series model for this one and this one. Okay? But the problem is you may have, let's say, 15 series to work with. Very tedious thing, right? But when you look at these two in this way, may be very different from viewing in another way, like this one. This is scatter diagram. Now, you see, the most of the variation, well, we've seen in a previous graph the plot of S1 and plot of S10, right? Separately. And S10 varies within this range, right? S1 vary within this range, right? But when you look at this, you know, most of the points are located along this line, right? Along this line. So these are our R1, let's say R2, and linear combination is this, psi1. And so, you know, actually what you're trying to do is to explain this variation and this variation, right? But when you create new variable as a linear combination of these two, such as this one, you know, this one varies this range and that range, right? So instead of working with individual series, you may be able to reduce the dimension of the problem by finding something known as principal component. Okay. So let's take a look at more detail about this one. The thing is then how to calculate these weights. You see, these are same data, right? How to find different numbers, different combinations. So that's the question of principal component analysis. And let me go back to the meaning of this one again. The way how to calculate this psi 1 as opposed to others. But here, if you use compact notation, weights are written here as a W, and data in matrix R, then simply, if you know this W or weights, then you can calculate this one. Right? On the other hand, factor analysis, well, you see the variation of historical data, right? Why this variable fluctuates? Because it has one common factor. Let's call it psi 1. So if psi 1 change, this will change, but the sensitivity is going to be different depending upon the value of C, right? Also, why R1 through Rn change? Well, because second factor, common factor, but with different sensitivity or factor loading, okay, and so on. So suppose there are k factors, then this is the way we set up this factor model. So you have data, and you try to find these factors. Okay. Looks similar, but the other way around, right? Suppose this is in fact all the stock returns listed in our exchange. And suppose you have only one factor. So these are all 0. There is a single factor. If there is a single factor, can you interpret what that might be? Why every stock return change? Because market change, right? So this could be something very similar to return on index, COSP. Right? So COSP return change, and something change more, something change less. Right? So actually, if you build a model using historical data, and if you can find the sequence here, assuming only one, and because this is a return stationary, so this is also in the same scale return. So if you accumulate this one, probably you will see something very similar to our COSP. Okay. But our focus, well, actually, when you try to estimate, let's say, this type of factors using data like this, you need the method known as state space model and Kalman filter, because this is unobserved, right? Unobserved. So you need model for that. But this one, if you have a data and if you find appropriate weight, then you are all done. You can calculate this easily. Okay? So let me go back to this factor analysis. Let's say, usually there are a large number of variables you are considering. But usually, these factors are much smaller. Number of factors are smaller. So why these vary? Because this common factor, because of this common factor, and then idiosyncratic noise, their own small variation, right? So if these k factors explains most of the variation, then this portion is going to be very small, right? Very small. But suppose n is 200, k is 5. That's the advantage, right? You are reducing the problem, dimensional problem, from 200 to 5. Because if you know these numbers, and if you can identify this, then, because you know that the variation coming from this part is small. So if you, let's say, if you model those smaller number of factors, and if you plug them here, then you can predict this one, right? So if you predict smaller sequences, number of sequences, and plug in here, then you can forecast this one with quite closely with enough of accuracy, because this is assumed to be very small. So if you look the other way around here in principal component analysis, you might see why we are doing that. So you have n number in your data set, n variables, and by finding this linear combination, you want to find some smaller number of principal components, but explains most of the variation in n variables. Okay? So if you have spot rates, change in spot rates, of course, it has to be stationary. If you find this number right, that's your F1, previous EBS file, F1. And if you find second one, and that's your F2, and the third one is F3, and of course, because you have many spot rates, you can go F4, 5, 6, 7, right? But in this framework, you need just 1, 2, 3, and this portion is very small. If that's the case, then you are reducing your problem from the dimension of 15 to, let's say, 3. Okay. So let's take a look at more detail of this. So for the moment, principal component analysis, this is the data, this is the weights you want to find. The way we find it is, this is principal component, right? How to find this one is actually, suppose you have n-dimensional return vector. So I say just a return vector, but whatever it is, as long as it's stationary, it's fine. If this is stationary, then you can calculate covariance, right? Let's say omega. Okay. And then what is this thing here? Well, that thing is, if you calculate variance of psi, well, then variance of W transpose RT, right? And this is a random variable. This is known. So what is the variance? We have pre and post multiplying W. Okay, so this is known. This result, the variance of this is this one. We use something called a Kramer rule in the literature. So this is the variance of that, right? Your principal components. And you want to maximize this variance. So the portion of variance explained by this principal component, you want to maximize this one with some constraint where, as you can easily imagine, there are numerous ways of of assigning numbers to these weights, right? So there are infinite combinations. So what you do is you want to make sure that the length of this is unity. So what I'm saying is this squared plus this squared and squared equals to 1. And this squared and summed it over equal to 1. So that's our constraint, normalization constraint. Then we can find unique set as a W. So solving this problem, with respect to W, first order condition, and do this. And it turns out that the finding this W is to first find, using omega, find characteristic roots or eigenvalue. So if you have n by n symmetric matrix, then you can calculate n characteristic roots or different name eigenvalue. We sort it from the largest to smallest first. That's first step. Then what is this one? Well, these are all from linear algebra. So if you're interested in, you can go back to the literature about the seeing section eigenvalues and the properties and so on. But here, what we're trying to get at here is, suppose you can calculate this n eigenvalues. And what is then that eigenvalue lambda? Lambda is actually the variance of psi. So actually you can show this one. So we know that I ordered psi as 1 through k, right? Psi 1 through psi k. With particular situation in mind, which is if this is 1, and if this is the largest one, and if that is the variance of that, well, actually, you're calculating the variance of first one and second one and so on. But when you look at this one, suppose I added this all lambda. Then what we can also show is it is the same as trace of omega matrix. Yeah, omega is a covariance matrix, and trace is the sum of main diagonal elements. So variance, 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 n variances, right? So this is total variation. Total variation is same as this one. So, what this number means is these numbers are like the variance of first variable, variance of second variable, third one, and so on, right? So total variance. You want to find psi that explains, let's say, the biggest to smallest. Biggest to smallest. So if you create actually n principal component, you can exactly match this variance, right? Right? But suppose you have smaller number, let's say up to 1 through k, then of course this is not going to be the same, right? But if you set this number to k, which is considerably smaller than n, but still if you are very close, that's the idea of principal component. Okay. So we know that this is a total variation, right? Total variation, and numerator is the variance of the first principal component, or ith principal component, right? So we usually calculate this statistic to show or to pick how many principal components are sufficient. So we'll get to actually examples, so don't worry too much. But let me show you a real example here. Let's say you have two variables. So covariance matrix is 2 by 2. It's matrix, right? This is a Gauss coding, which I believe is available from our site. Let's see. So if you start GAUSS installed in our PC lab, and if you have file like this one, you can open it, or you can create this one, which is just a plain text file. Okay. And this is text file, narrow text file, where I write these things. Okay. So what is the first one? Well, this is the way we define matrix in Gauss. This is curly braces. Two numbers separated by comma, two numbers, right? So when you are done, then semicolon. And if you type X and semicolon and enter, if you run these two lines, then this is going to be your result. So these two numbers this way, these two numbers that way. Okay. How to calculate eigenvalue? Well, you have to go through complicated calculation. But don't worry, there is a function available from Gauss, this function. So if you plug in your omega there, then it will return those four numbers. What is the first number? This one, for instance. This one, I can type this, and if you run this line, then you will get this result, this result. Or if you type this VAR, this will return eigenvalue, lambda. Okay. Go back to this one. The same. Lambda 1 and lambda 2. Lambda 1, lambda 2. But in this way, in this case, in Gauss, it returns smallest one, the next one, right? So this is the largest lambda, and this is smallest lambda. If you go back to your linear algebra textbook, for each eigenvalues, you can find vector, eigenvector. For this one, for this one, and this one. So this function, if you want to receive eigenvalues and vectors, you type it this way. So 1, 2, 3, 4, right? But you have these as well, right? What these means is there could be some imaginary number situation. So this is imaginary part. But in our application, we don't see those imaginary part. So these two corresponds to our answers. So actually, this one, these two numbers, because we have only two variables, right? So these two are W weights to principal component that corresponds to this one. These are the weights. If you multiply these two numbers to those two data, then that will make the second principal component. So these are weight, those numbers, first weight, and this one is the second weight. Actually, if you square this and square that and sum it, and this is the result. You see, normalization means the length is 1. And this is lambda. These are lambdas. So if you sum these two numbers in a vector using command sum C, and this number is 0.10. 0.10 is you see our covariance matrix omega, and this DIAG function is just picking main diagonals, and then sum it. So total variation is this, and if you add these two numbers, the same thing. So hopefully you get some sense on principal component. So if we go back to our original problem, you have n variables, okay? And you can calculate covariance with dimension n times n, right? Then you can calculate n number of eigenvalues and corresponding eigenvectors, right? There, the first one, if you look at the largest eigenvalue and its corresponding eigenvectors, those numbers, vectors are these numbers. Eigenvectors that corresponds to second largest eigenvalue will determine weights to psi 2 and so on. So this is the EBUS output. From previous example, we calculated using GAUSS two eigenvalues. One was this, the other one is this, right? But when I tried the same thing using EBUS, it reports same number. Of course, the method is the same. Right? So two numbers, check it out. And what it says is, because you have two series and you computed, you are looking at two lambdas. So when you add these two, then that should explain all variance, right? So what it says, this one and this one, well, actually, the total variance of these two variables, the first principal component explain about 89%, almost 90% of total variation. The second one explains about 10%. So in sum, if you have these two, then 100%. Okay. So if you think that about 90% explained by first principal component is sufficient, then you can set k equals to 1. Okay. Let's take a look at the other, this one. So let's say you have data with these maturity. These all spot rates. And read it, let's say, using this name. Okay. So in our example, our sample EBUS file, these are S1, S2, S3, S4, and those. First thing is to calculate change, to make it stationary first. Okay. So make RT as a stationary series. Okay. So when you're all done, there are 18 maturities. In EBUS, you can calculate using sequence, and this is actually the output. See, eigenvalues, the first one, the largest one in this particular example was 15, and then 1 point something and 0.37 gets smaller and smaller, practically 0, right? So because there are 18 maturities, you can go all the way up to 18, right? But we know that, you know, cumulative explanation by first principal component explains about 85% of total variation, and first and second all together about 94%. So second principal component explain about 9%. And the 3, 1, 2, 3 explains about 96%. And we say this is principal component 1. Well, if you have a data like this one, data, and this is the eigenvalue corresponding eigenvector. So if you multiply this and sum it, and that will give you this number. See? So value at t multiplied by this one, and value of principal component at t. Value at t plus 1 multiplied by this, then value at t plus 2, t plus 1, I'm sorry. So t plus 1, 2, 3, 4. You can calculate this sequence. Right? If you want to find, let's say, F2 sequence, in our previous example, data is multiplied by the second weights. F3 variable, which is principal component number 3, is this times that. And I think, you know, 96% is more than enough. Then forget about it. So if you calculated our principal component, what is the interpretation? Well, suppose you define series as slope as long maturity yield, and the difference between long and short maturity spot rates. That's my particular version of slope in this example. What is, then slope is usually, because this is I1, non-stationary. Usually the change is also non-stationary. So the difference is non-stationary, so we take change. So let's create this one using historical data. And also, what is curvature? Curvature is to compare, you know, two numbers, straight line, and this number and that number. This is curvature, right? If this is the same, then straight line. If this is positive, then this is curved like that, right? So I pick 2, 3, and 120 months, so 10 years, and 3 months, and 2 years to calculate this, and also I take difference. Okay? So I have probably the reason why I bring this one as this version is, somehow when I create PDF file, this one doesn't show up. So I want to show this one. So these are principal components 1, 2, 3 generated from previous procedure. And this is the change in slope, change in curvature, and I pick any series. Let's say S24 or S36, 36 months, 3 years, and then take the change. So change in particular maturity spot rate, and change in slope, change in curvature, and this one, and calculate a correlation. So the first principal component, is it more likely to be representing slope, curvature, or level? The second one, slope. The third one, curvature. So we interpret these three, even though we calculate this one from just pure computation, but we can interpret this one as a level factor and slope factor and curvature factor. Assignment 2 is right here, but I didn't cover it yet. So don't worry about assignment 2. When I finish this up, then you can start your assignment 2. This one and one in the previous slide, and the due is week from that day. Okay, so let's come back to this one next time. And I will show you some of the future, like principal component analysis. Okay, so when you come back to this, when you come back next Monday, then I try to play with this one a little, and to give you more idea about principal component analysis. So this is very simple, but still very powerful and have many applications. So having correct understanding is very important. If you feed in some data and it'll produce some output, but if your procedure is incorrect, then all goes wrong. So you have to understand it 100% correctly. So there shouldn't be any doubt in your exercise. So let me come back next time. Okay? Questions? Comments? Okay. I checked these classes well taped and linked to our portal. So just in case, if you want to try something again, then you can always go back to that link. Okay, thank you very much. This is it.